Hello, everyone. This presentation will cover sickle cell disease, its molecular mechanisms, and a novel approach to using a HIF prolyl hydroxylase inhibitor that I researched in the town sickle cell mouse model. Before that, however, I am Suchir Ryali, a rising senior at Lafayette High School in Wildwood, Missouri. I'm a student researcher at a few labs, involved with science and leadership in my school and community, and I'm passionate about neuroscience and its intersection with oncology, hoping to kind of pursue that in the future. So, sickle cell disease is a major global health issue that transcends national borders. It affects over 20 million worldwide, and looking at this chart, you can see that a lot, and specifically 80% of that burden, falls in sub-Saharan climates of Africa. There is some speculation that the sickle mutation provides resistance against the malaria pathogen. In the United States alone, sickle cell sums to over $1.5 billion in healthcare costs, and in regions like Africa that have 100 to 300 times less healthcare spending, we see complications arise within the disease itself, but also within patients who are not able to invest in expensive treatments like gene therapies. So, kind of very briefly to begin, sickle cell disease is a hemolytic anemia, meaning red blood cells are destroyed faster than the body can replenish them. Most commonly, sickle cell disease is associated with the notorious sickling of erythrocytes, which often causes blockages or occlusions leading to acute chest syndrome, strokes, and organ damages. We can see many organs damaged, the lungs, the brain, the kidney, the spleen, but very frequently also is the liver. In fact, we see about 10 to 40% of sickle patients developing some sort of liver disease, and 30% of these sickle-related deaths included hepatic or liver causes. So sickle cell disease is caused by a point mutation in the human beta globin gene. Particularly on the 11th chromosome, we observe a shift from glutamic acid to valine. This mutation changes the structure of hemoglobin, which we call HbS, the abnormal hemoglobin. When both parents pass on this HbS as a homozygous mutation, the child is then positive for sickle cell. At physiologically low oxygen concentrations within tissues, the abnormal hemoglobin molecules undergo a conformational change, which causes red blood cells to deform into a sickle shape. In this image off to the right, you can see that although there are many regularly shaped erythrocytes, there are many abnormal and sickle ones as well. Sickled erythrocytes can sickle and unsickle a few times, but after many times, it becomes an irreversibly sickled cell. There are oftentimes essentially very sticky cells, and they stick to the microvasculature in organs like the liver, which blocks blood flow or causes ischemia. We then observe rupturing and inflammation, all due to this vaso-occlusion. So, in this simplified liver on the left, there are a few different vessels: the hepatic artery branch, sinusoids, and the central vein. Generally, the sinusoids are occluded with sickle cells as they are smaller vessels. When this happens, the liver can't get blood from point A to point B, causing ischemia. When oxygenated blood can't reach the liver to its fullest extent, the liver then stops receiving oxygen and nutrients, and we see necrosis or cell death. Within the liver, we observe ischemia, necrosis, and then fibrogenesis in that order. So we can see fibrosis or fibrogenesis and thus necrosis by staining for collagen in a Masson trichrome stain. So how can we prevent this necrosis? Well, one way would be to create more red blood cells, because then we would see an increase in oxygen uptake. So in the past, there have been many erythroid-stimulating agents approved on the market. These agents stimulate erythropoietin or EPO, which stimulates the bone marrow to produce more red blood cells. However, a relatively newer and less tested outlet for treatment is through a prolyl hydroxylase inhibitor, which also stimulates EPO, but it also stabilizes the hypoxia-inducible factor or HIF. So the medication treatment I use preclinically is FG4592, which is a hypoxia-inducible factor prolyl hydroxylase inhibitor. What does that mean? Normally, an enzyme called prolyl hydroxylase quickly breaks down this protein called HIF, which helps to regulate EPO. But in hypoxia, this enzyme is less active, so HIF is not degraded. So if we're on the top of a mountain, for example, in a hypoxic condition, our body is going to start producing more EPO and thus more red blood cells. Back on the ground level, inhibiting the prolyl hydroxylase then doesn't degrade the HIF, and thus we produce more EPO and more red blood cells. We can actually see that in past studies, as a mouse treated with FG4592 has a significant increase in RBC count compared to a carrier or a control. So based on the improving of the hematologic parameters, we then hypothesized that it would be associated with a decreased hepatic ischemic injury or necrosis in FG4592 treated sickle mice. So we treated these sickle mice with a 50 mg per kg FG4592 dose or a olive oil carrier equivalent dosage 3 times a week for 4 weeks. We then took samples of the liver to analyze. I then performed a Masson trichrome stain using a Bibrick scarlet acid fusion solution to highlight the collagen for fibrosis. You can see an example of this in figure A, where there is this general area of fibrosis in blue surrounding the vasculature on the liver. I then used a Leica microscope at 5x to take numerous pictures and piece them together very carefully. Once I had a full sample, I used the NIH's image J to quantify necrotic areas. You can see a general example on figure B here on the right here of the threshold. So specific to the project, what are we looking for? So based off a hematoxylin and eosin stain, we can see a mouse that does not have the disease on the left compared to the middle. Evidently, there is a huge difference, as you can see this big splotch of necrotic area around the portal triad. On the right, the trichrome stain brings these colors out, and you can see the necrotic area in purple. So what did I see? In carrier samples or olive oil controls, I saw a 32.65% necrotic rate, with consistent necrosis around the tissue. I highlighted those regions in red to be very distinct in these images. On the right, on the FG4592 treated mice samples, I saw a 12.78% average necrotic area, with a huge visual decrease in overall necrosis. So this was extremely significant, as you can see on the chart on the right. The ImageJ quantification of hepatic necrosis due to that HIF treatment showed a significant decrease. So we can say that the Town sickle mice treated with FG4592 have an overall decrease in hepatic necrosis. So based on this conclusion, I speculate a few things. First, I believe that there is increased red blood cell production from the stimulation of EPO pathways. As FG4592 stimulates the EPO pathways and prevents the degradation of hypoxia-inducible factor, the decreased necrotic rate is only evidence of increased oxygen uptake. Secondly, I speculate that there is less tendency for sickling to occur, as I believe there is less vaso-occlusion in the hepatic portals and the sinusoids is reason for there to be lessened necrosis. In the future, I'd like to continue by observing other affected organs like the spleen, which has a general very defined structure which degrades under these sickled conditions. Before I close out, I'd like to thank the Fleming Laboratory at St. Louis University for allowing me to research there the last 3 years and to lead this project. And I'd like to thank you for watching this presentation. If you have any questions or comments at all, please feel free to reach out. I'm available on LinkedIn and you can also email me. Thank you again.